What's going on, everybody? In this video, I want to talk about how we can solve linear inequalities as well as absolute value inequalities. These are the easiest types of inequalities to solve, and I'm going to show you the processes and methods that we use to solve for these types of equations easily. So let's get into some examples here. Okay, for this first example, I have 3 times x plus 2 plus 7 is less than 2x minus 5. So the process that we're going to use to solve this type of inequality is the same process that we use to solve linear equations. You clean it up, isolate x, and then solve for x. Exact same kind of format. You're going to be seeing some familiar operations for this one. So the first thing that I'm going to do is I'm going to distribute the 3 on the left-hand side. So the 3x plus 6 plus 7 is less than 2x minus 5. And then I can clean up the 6 and the 7 on the left-hand side too. So 3x plus 13 is less than 2x minus 5. And so the next thing that I'm going to do is I'm going to focus on getting the x's on one side of the inequality. So I'm going to do this by subtracting a 2x from either side. And so I end up with x plus 13 is less than negative 5. And then now that I have one singular coefficient in front of x, and I can move the 13 over to the other side to isolate the x term. And I end up with x is less than negative 18, and this is going to be the answer to this inequality. So this is what makes inequalities different than equations. In an equation, you have one set solution that x can be. X is equal to this, and that's it. But in an inequality, you have an interval of values that will fit the criteria to solve this inequality. So if you want to represent this with an interval notation, take note at the type of inequality symbol we have. We have a less than. So since we have a less than symbol and it's unbounded, we have negative infinity for the lower bound. Because x can be less than negative 18. It's every number that's less than negative 18. So we know that negative 18 is the higher bound. And since it's just strictly less than, it is not included. So we represent that with parentheses. And if you want to graph this, you draw out the number line. And I have a 0 right here. And then negative 18 is going to be somewhere over here. So x can be any value that's less than negative 18. So we represent that with open parentheses, and then every number to the left of this value is valid for x. So in the next example, more of the same kind of thing. The first thing that I'm going to do is I'm going to distribute on both hand sides. So I have 2x plus 14 minus 4 is greater than or equal to 5x minus 15. And I can combine the 14 and the negative 4 over here. So I just have 2x plus 10 is greater than or equal to 5x minus 15. So the next step for me is to get x on one side. So I'm going to do that by adding a 2x on, or so I'm going to do subtracting 2x on either side. So I have 10 is greater than or equal to 3x minus 15. And then the next step is to just isolate the x fully and then divide through to get just x and an inequality. So I have 15 to add on either side. So I have 25 is greater than or equal to 3x, and so I just divide by 3, and I have 25 over 3 is greater than or equal to x for my answer. And so what I'm going to do now is represent this with interval notation. So I know that x can be every number that's greater than or equal to 25 over 3. So 25 over 3 is the lower bound, and it's included, and x can be any number greater than that. So I represent that with an infinity symbol. And then to graph this, draw out the number line, I pick out 0 from my reference, I mark 25 over 3 on the line, and then I see that I have a greater than or equal to symbol. So I'm going to have a bracket facing to the right, so that every value that's to the right of 25 over 3 is valid for x. Okay, so in this next example, I have 4 times 5 minus 2x is less than or equal to 1/2 times 8 minus x. So the process is going to be the same even though I have coefficients that are fractions. It's not a big deal. We still have the same process. Don't let the fractions in there trip you up because we're going to be doing the exact same procedure. So first thing I'm going to do is I'm going to distribute. So I have 20 minus 8x is less than or equal to 4 minus 1 half x. And then what I'm going to do is I'm going to get x on one side. And I'm going to do this by adding 8x because it's going to avoid me having negative coefficient in front of the x later. So when I add, I end up with 20 is less than or equal to 4 plus 15 over 2x. And then I subtract 4 from either side. And when I do this, I have 16 is less than or equal to 15 over 2x. And then the last step is to just divide both sides by 15 over 2. So I have 32 over 15 is less than or equal to x for my answer. To represent this in interval notation, I see that x is every number that's greater than or equal to 32 over 15. So I have a bracket and I know that 32 over 15 is the lower bound. Since x, this is an unbounded interval, I have infinity for my other endpoint, and this is what it's going to look like in interval notation. So to graph this, I have my number line with 0 as the datum, then I plot 32 over 15 on the line, and again, I have a bracket for this as the lower bound, and then x is every number to the right of 32 over 15 on the number line to represent greater than or equal to. This one, I have 1/2 times 3 minus x is greater than 1/3 times 2 minus 3x. Again, the process is going to be the same. Don't let the fractions throw you off. If you have to use techniques to combine fractions together, then you can do that within the context of solving the inequality. There's layers to these types of problems. So the process is going to be the same, but the approach might be slightly different because we have fractions in there. So 1/2 times 3 is going to give me 3 over 2. And then 1/2 times minus x gives me a minus 1/2 x. And we have greater than. 1/3 times 2 gives me 2/3. And then 1/3 times negative 3x gives me a minus x. And so what I'm going to do is I'm going to add an x to either side because this avoids negative coefficients again. And so I have 3 over 2 plus 1/2 x is greater than 2 over 3. Next, I'm going to subtract 3 over 2 from either side. So I'm left with just 1/2 x is greater than negative 2 over 3. And then, of course, just divide by 1/2 on both sides to get your answer of x is greater than negative 4 over 3. So this represented with interval notation, I'm going to have x is every number greater than negative 4 over 3. And it's not included, so I have a parentheses, and negative 4 over 3 is the lower bound. And x can be any number greater than that. Represent this on a number line. I've got 0 as my reference, negative 1. Negative 4 over 3 is going to be somewhere over here. And x can be any number greater than that. So I have the parentheses facing to the right, open, and then every number to the right of this value is the valid answer for x. But what if I had something like this? So I have the absolute value of x minus 3 is greater than 4. So much like what we were doing to solve absolute value equations, we're actually going to use the definition of absolute value to create two separate inequalities. So we're going to have two inequalities to solve for this. In the first case is in the event that value inside the absolute value is positive, so we just have x minus 3 is greater than 4. And then to accommodate the other scenario, in case this is negative on the inside, we have a minus x minus 3 is greater than 4. And then these are the two inequalities that we're going to solve. So the first one is simple enough. You just add 3 to both sides, and you have x is greater than 7. And in this other one, something interesting happens. When we divide through by this negative, we have to switch the inequality symbol because what we're doing whenever we divide the negative is we're essentially flipping all of the signs. And when you flip all the signs, you have to flip the inequality statement to make it consistent. So what we're going to do is x minus 3 is less than negative 4, which is equivalent to the original inequality that we had. So, and then you just add 3 to both sides, and you get x is less than negative 1. So notice this, it's not possible for one x value to be both less than negative 1 and greater than 7. It doesn't make any sense. So what we're going to do is we're going to make an interval representing both of these solution sets. So x is greater than 7. 7 is our lower bound, not included, and x is every other greater than that. So this is represented with this interval. And then the second one, we have x is less than negative 1. So negative infinity, lower bound, and then negative 1 is the higher bound, not included. So if you want to represent the entire solution set that x could be, we have to unionize these two intervals. So I have the smaller one first, negative infinity to negative 1, and I unionize it with the other interval. And this gives me all of the values that x can take on. And so if you want to graph this, we do it similarly. I have my number line here. I'm going to mark negative 1 and 7. So the first interval states that x is every number greater than 7. So I'm going to draw a parenthesis sign on 7 and then highlight every number to the right as a valid x value. Then the second interval states that we have every number that's less than negative 1. So I'm going to draw parentheses facing to the left of negative 1, and then every value to the left or less than negative 1 is a valid for x. So every number in between negative 1 and 7 is no man's land. It does not represent x. Okay, this is the last example that I'm going to do today. So again, we have absolute value inequality, so that's going to stem two inequalities from us. The first one is the event that the inside of absolute value is positive, so we're going to have x minus 3 over 2 is greater than 3 over 2. And then for the other scenario, we have minus x minus 3 over 2 is greater than 3 over 2. And then we just solve each inequality separately. So the first one's simple enough. You just add 3 over 2 to both sides, and you get x is greater than or equal to 3. And then when you divide through by the negative, you end up with x minus 3 over 2 is less than minus 3 over 2. And notice what we have. We have a minus 3 over 2 on one side and a minus 3 over 2 on the other side. So they're going to end up canceling. And then I just have x is less than or equal to 0 for my second interval set. So the first one says that x is every number greater than or equal to 3. So no 3 is my lower bound included. Every number after that is the infinity. And then for the second solution set, x is every number that is less than or equal to 0. So know that 0 is the high bound, negative infinity to 0, and the 0 is included. So to unionize these, I have the small interval first unionized with the larger interval here. And this is all of the values that x can take on. And this is the entire solution set. And then to represent this graphically, I have my number line, the 0, and the 3. And so every number greater than or equal to 3, I have my bracket facing to the right, and every number greater is an x value. And then every number that's less than or equal to 0, it's also a valid x value. So this gap right here are not valid x values because they're not included in the solution set. So I hope this video was clear about how we use the methods of absolute value definition and the methods to solve linear equations to solve these kinds of inequalities. The only thing that's really different is the solution. Instead of just having one concrete answer or maybe one or two concrete answers, we have entire intervals of infinite numbers that x can take on. So I hope this video was helpful. Thank you guys for watching. Take care, everybody.